everybody. Today we're looking at still bonding, but we're moving on from ionic bonding into covalent/molecular bonding. We really use those two words interchangeably, covalent and molecular, and we'll see why in a second. But the big idea to take here is, whereas ionic bonding happened between two atoms that were transferring electrons, so one atom gave the electrons, the other atom took the electrons, that transfer was there. A covalent bond is specifically between atoms that share electrons. So they're actually going to be sharing the same electrons. Also, in ionic bonding, we saw that ionic bonds happen between metals and nonmetals. So a metal on the left side of the periodic table, a nonmetal on the right side of the periodic table. In a covalent bond, that bond is actually formed between nonmetals. So really over here on the right side of the periodic table, within there. And sometimes metalloids as well. So those that are on that stair-step, that red stair-step line. So mostly we're working with atoms that are on the right side of that periodic table. Now, why are covalent bonds forming? The same reason that ionic bonding happens, and that's to satisfy the octet rule, right? So the sharing of electrons is going to happen so that atoms feel like they have the noble a noble gas configuration. So they feel like a noble gas, or they have that electron configuration of a noble gas. All right, so I mentioned that we call covalent bonding also molecular bonding. The reason really comes down to the smallest representative particle of a covalent compound being called a molecule, right? So when we talk about molecule, we're talking about a bond formed between two or more nonmetals or metalloids where sharing electrons is happening. Remember that for ionic bonding, the smallest representative particle, not a molecule, but a formula unit. So for ionic bonding, we have formula unit. For covalent, we have molecule. We have 7 diatomic molecules, which I want to point out just before we go any further. And these are specifically molecules, so again, they are between nonmetals, and they're formed when atoms of the same element share electrons. So oftentimes we'll have covalent bond formed between two or more different nonmetals. Diatomic molecules are bonds formed between the same atom. Okay, so H2 is a bond formed between two H's. N2 is a bond formed between two N's. O2, two O's. They're still sharing electrons, and the key here is that these 7, there are 7 of them, these 7 diatomic molecules, they are never found as individual atoms, not ever. They're either going to bond to a different atom, or they're going to bond to themselves. That's it. You're never going to find N anywhere by itself unless it is bond to another atom, a different atom. So it's either bonding to itself or another atom. So the way to remember these 7, to write the formulas for them. So if I ask you the formula for nitrogen, it's N2. For oxygen, it's O2. It's not O, it's not N. These 7 form a 7 on the periodic table, just like this, plus hydrogen. But they form a 7 on the periodic table starting with atomic number 7. So if we look and we find atomic number 7, we see that it's nitrogen, and they actually make a 7 going down the halogen group. Okay, so there's 6 of them right here. The 7th is hydrogen up in that corner. Right, so just keep that in mind because we are going to be naming molecules today, binary molecules. These are some of them that we have to know how to name, and they're a little bit different than our typical naming rules. Now, covalent compounds are molecular compounds. I want to get into a few properties of them since we've talked about the ionic properties. Whereas ionic compounds are usually solids at room temperature, molecular compounds can be any state of matter at room temperature. They can be a solid, they can be a liquid, they can be a gas. They have relatively low melting and boiling points. What do you think that says about the strength of the attraction there? Ionic bonds have really strong attraction and high melting and boiling points. Covalent or molecular compounds have less strong attraction, and so it takes less energy to break those bonds to melt or boil. So relatively low melting and boiling point. And then they don't conduct electricity in their pure state. When dissolved in water even, they're not going to break up into ions like ionic compounds. And because they won't break up into ions, they're not really good electricity conductors. So we're going to take a look now at how to name covalent compounds. So there are a few rules, but I will say that nomenclature for molecular compounds is easier than for ionic. We're only going to be naming binary molecular compounds. Now remember, the bi here means 2, okay? So these are molecular compounds that happen between 2 atoms, not more than 2, okay? Our rules here, and we'll go through them kind of one by one. The first 2 are just like we saw with ionic bonding. The first element, the name stays the same. Same way that we did it with ionic bonding. The second element, the name ending changes to "ide," just like we saw with ionic. So we have stem plus "ide." Okay, so same as ionic. Now here's where we get different, a little bit different than ionic bonding, and the next 4, 5 are all different from ionic. We're going to use prefixes, and this is what actually makes it a little bit simpler to name molecules. We're going to use prefixes to indicate the number of atoms. Okay, so prefix means it goes on the beginning of the word. So if we have 1 atom, we call it mono, whatever the element is. 2 is di, 3 is tri, 4 is tetra, all the way down the table to deca. Now, we kindly put these on the back of your periodic table. So if you're ever wondering what the molecular prefixes are, they are listed on the back of the periodic table there. The exception here with those prefixes is we don't use mono on the first element. So if the first element only has 1 carbon, we don't call it monocarbon. Okay, we would just call it carbon. We'll use mono if the second element, there's only 1 of that atom, but not on the first, and we'll see some examples. We will drop the prefix A or O before oxygen, and this is just kind of so that it sounds more proper. So we would say monoxide, not monooxide, if we have 1 oxygen. We would not say hexaoxide if we have 6 oxygens. We would say hexoxide, and it just rolls off the tongue a little bit easier. We never reduce formulas. So remember that if you have an ionic compound and you have like 2 magnesiums, no, that won't work. Yeah, 2 magnesiums and 2 sulfur ions forming, those 2's reduce to 1. So you wouldn't have Mg2S2, you would have MgS. Here, we never reduce the formulas because these prefixes tell us exactly how many of each atom we have, okay? And then our exceptions to these naming rules, which we're going to put to use here in a second. H2O, you hopefully know, is called water. We don't refer to H2O as dihydrogen monoxide. You can, but it's water. Actually, you can't. Don't call it dihydrogen monoxide. It's water. And then NH3 is not nitrogen trihydride. It is ammonia, okay? Those are just some exceptions to our naming rules. Now let's try these out. We have N2O. So I have 2 N's here. So I'm going to look at the prefix 2, and that's di. So this is dinitrogen. Now remember, the first element, the name stays the same. So dinitrogen, and then we need the prefix for 1O. Well, 1 is mono. We don't use mono on the first element, we do on the second. So this is the second element, we will use mono. So this is monoxide, not monooxide. Remember, we drop the A or the O before oxygen. The second one, SiS2, this is silicon, right? There's only 1 silicon, and we look over here and we see that 1 is mono, but we don't use mono on the first element. So this is not monosilicon, it is simply silicon. The second one, we have S2. Again, we look over here, 2 is di. So we're going to have disulfide, right? Remember the second element, just like the ionic compounds, we change the ending to "ide." So we have monoxide, disulfide, okay? That's it for naming. Again, it is quite a bit easier than ionic. It will get complicated when we add the 2 together. But the last thing I want to look at is a specific subcategory of molecular compounds. And these actually do conduct electricity, but they're like the only molecules that do. But these are inorganic acids. They're molecular compounds that actually, when you dissolve them in water, they will dissociate, which means they'll split into smaller particles. And these smaller particles that they break into are actually ions. They'll break into a hydrogen ion and an anion. They're still not ionic compounds. They are molecular compounds made up of only nonmetals, but when they dissociate, when they're dissolved in water, they do break apart into ions. Now we're going to see these more in second semester, but I want you to be able to recognize that you're working with an acid if you see it. And the keys to knowing that you have an acid is that, here's the formula, they always start with an H, right? They're going to break down into an H plus ion eventually, so it makes sense that it starts with an H, all right? So you'll always have an H in front. Hydrogen is H. I should maybe put hydrogen. You'll also always see, next we have an anion. So it's hydrogen bonded with an anion, a negative ion. But the other giveaway besides the H out front is the aqueous in the back. Now hopefully this makes sense because we said dissolved in water. So it should make sense that this state is aqueous because it's been dissolved in water. It's not an acid unless it's been dissolved in water. So we'll always have AQ at the end. Now the last thing is just, these are the most common inorganic acids that we work with really in chemistry, but also in our chemistry class. I do want you to have an idea of them, and you are going to want them on the back of your periodic table. So write them on the back of your white periodic table at some point. You'll also want them on your note card when we get to the final exam. But HCl, aqueous, we call hydrochloric acid. HNO3, nitric acid. HC2H3O2, acetic acid. H2SO4, sulfuric acid. H2CO3, carbonic acid. And H3PO4, phosphoric acid. I can tell you how to name these if you're interested, but I'm not going to put it in this video. But come see me and I'll tell you a little bit about how we name these. It's not too complicated. All right, that's it for molecular bonding, covalent bonding. Remember, they're interchangeable. And we will keep on going with bonding in class.